Section 10.4 focuses on finding the derivative of a function using the limit definition of derivative, which involves using the difference quotient.
So Q1 is when x is equal to 4. You will draw that secant line right there, like that. And we want that slope. As a reminder, does everyone remember what the formula for slope is? y2 minus y1 over x2 minus x1. It's also known as the difference in the y's over the difference in the x's, where we have used delta to represent difference, right? It's a scientific thing. It's delta y is the change in the y's, delta x is the change in the x's. Okay. The other way to express this is if you have a function, then y2 becomes the function value at the given x point. So if I'm still using x2 and x1, then this is f of x2 minus f of x1. And so that's what we're going to do here. We want the slope between p and qi. I know the x is 4. So we're going to figure this up. We're going to compute it here. So it's going to be f of 4 minus the x value on the p point is 2. So it's minus f of 2 over 4 minus 2. Now, there's a shortcut way of doing some of these things in your calculator. If you want to take a look at that real quick. So first thing, go ahead and go into y equals and plug in the equation of the function that we're looking for, 0.25 x squared. And then go to the second table set. Make sure your table is set to ask, because we're going to ask it about these different values. Okay. So this is method 1. I'm going to show you both methods here. So if I go to the table, let me clear out some of these values here. Delete, 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 delete. Okay. And the first x value we're working with is 4. So when x is equal to 4, the y value is 4. That means along that curve, when x is 4, the y is 4. So on your page, f of 4 is 4. I'll write that down. Then compute what f of 2 is. F of 2 is 1. So we have 4 minus 1 over 4 minus 2. That's 3 over 2, which is 1.5. So that's what we have for this first. And that's just if I plug in the y function value as it was. All right, that's one thing you can try to do. The second one, let me show you this. You're going to like this as well. All right, go back to y equals and leave the y1 alone. Go down to y2. Okay? The calculator has a method for calling up the function values from previous functions. Okay? Now, right? And this is y1. This is y1. If we want the slope, right, the slope is f of x2 minus f of x1. But in this example, x1 is fixed. What is the value of x1? It's 2. So we're just going to put in f of 2. And then this is x2 minus 2. This is fixed for this example, right? Because we're always leaving p by itself, and we're moving the q points. Right? Right here. P is fixed. This point is going to move and create different secant lines, but they're all emanating from P. Is that clear? So what we can do here is, if we know that y1 is our function, f, then you can actually tell the calculator y1 of x minus y1 of 2 over x minus 2. Okay. Let me show you how to do that. If you'll look right here near the arrow keys, there is a button called vars. Okay, so while your cursor is on y2, you can go to vars, tab over to y vars, hit function, and call up y1. You'll see that it's on y1 already, so I just hit enter. Now that calls y1. Now this works exactly like a function f. You now have to tell it of x. So it's parentheses, x, close parentheses. Okay. And then minus, and we'll do it again, and we'll call it y1 of 2. So vars, y vars, function vars, y1 of 2, close that. That's how you produce the function values on the calculator. Now this is the numerator. I need to go back. Let me show you how to go back here. This needs to be inside of one big set of parentheses. So I'm going to go back to the front. I'm going to insert. So second insert, left parenthesis. I'm going to scroll to the end here. I'm going to close the numerator, divide, and then I'm going to open the denominator and then do the bottom part here, which is x minus 2. Close. All right. And now you can go to second table. And now the y2 column is the slope. Right? So y2 is now equal to the slope. So you can produce all of these calculations for your table just by plugging in the appropriate x values in the chart, and then you can put them in the thing. But I want you to understand where all this is coming from. You are computing slopes. Okay. All right, so go ahead and complete the chart, and then answer the question at the bottom. What are you talking about? So, what you can just keep doing it. Yeah. Come up with the general form. Okay. Yeah. So all you're doing is finding the word.
All I did was with the same thing you did. Exactly.
225 is this S3. Okay. So 225 minus the y. So I just 1. So you have 2 is 1. And those are y. Okay. Well, it's a formula. You can do it fast. So this is a formula. This is a bunch of them. And that's you can simplify that down to a lot. F of 2 is 1.
Oh, from over here, right?
Yeah, so
Okay, so then we look at
well, F of 2 is 1.
the F of 2 would always be 1. And it would be 1 F of 2 or no?
No. That's
Oh,
a y
because
value.
it's the F of
Because that's the x value.
Okay.
Yeah, let me make sure everybody's on the same page here. So for Q2, the x value is 3. I don't know why it doesn't focus automatically. It should. So it's 1.25. So you should end up with 1.25 for Q3. Now you can either use the calculator to do this, or you can do it by hand. If you're doing it by hand, then what would you have? Right. You would have f of 3 minus f of 2 divided by 3 minus 2, because you're finding the slope. So you would plug in 3, so it would be 0.25 times 3 squared minus 0.25 times 2 squared over 3 minus 1. See, remember, if it says f of 3, that's the y value from the function when you plug in 3. Okay, it's not just a 3. And then f of 2 is the y value when you plug in the 2. And then you work all this out, and you can get 1.25.
Are you using the 1 on the bottom?
Sorry. Is it 1? It's 2. It's 2. I'm sorry. It's 2. It's 2. Okay, 1.25. And then for the last box, you have to do the formula because the calculator can't do it. It's just in general x. So work it with f of x. Simplify that. total answer. Subtract that minus 1. Okay, so let's check some of these answers and see if they all came out right here. So you should have gotten 1.25 for Q2, and then 1.125 for Q3, 1.0625 for Q4, 1.025, and then 1.0025 for Q6. Now if we do the formula, this would be f of x minus f of 2 over x minus 2, which is 0.25x squared minus 1 over x minus 2. And that's it. Yeah.
You get to type it in the calculator again with the union of bars.
With the bars, you just go to bars, y bars, function, and then y1. Bars, and then are you tabbing over to y bars?
Yes, sir.
And then you see how it's highlighted right here on 1, and you just hit enter, and then you pick any of these right here. One. Yeah. By the way, this y bar stuff works in the home screen too. You can do bars, y bars, function bars, 1 of 4. Well, let's do 3 of 3, and I'll tell you the answer. You can actually just type that in anywhere. On some calculators, watch this, if you have this. If you do the alpha and then the 4, it comes up with a shortcut list of the y bars. So you can just do it that way. Some calculators work, some calculators don't. I haven't figured out if it's like a BIOS thing, like certain calculators were produced after a certain time and some of them do it and some of them don't. I don't know what's going on. Mine does it, but a lot of the students I've had, theirs do not. Okay, so the question here is, you see we're creating all these secant lines. Here's the next one. And then here's another one. And then here's one right here. And then everything. And eventually we get to the tangent line, like that. It's not drawn very well, but that is what it is. So the question is, what number is the slopes of the secant lines approaching? So what number are we trending to here? We're trending down to 1. All right, let me show you the model on the computer here that I've built. So here is the current scenario. Check mode. All right. here is the original parabola, and then here is the secant line that goes through the point where x is 2 and x is 4. And here's the table. When it was 4, then that slope was 1.5. Now, what you're watching here is I'm going to move the x value of this point down the curve. And watch what happens to the secant line. What happens to the secant line? Well, it disappears at 2, which is no good. But we can certainly get close to it. Right? And we can have the table that mimics all of these values if we want. 2 would be undefined. How about 2.5, 2.25? What did we do? 2.1, 2.01. We can even do 0.01, 0.1, like that. Oh, it didn't like that, did it? That's the same one. So it's clearly getting closer and closer to 1. But if we try to do 2, it's undefined. And that's a problem. So what do you need in order to do when the 2 points converge, when the 2 points meet? Calculus. This is the reason calculus was invented, right here. Because you're trying to get the slope of a line when that line only has one known point. You remember from geometry, how many points make a line? You need 2 points, right? Well, until you get to calculus, you had to have 2. But when we have the calculus tools available, then we just need it at 1 point. That's basically what this course is about, is finding that slope. And that slope is called the tangent line. Okay, so these things are going to converge to what we call the tangent line slope. All right. So let me give you the overall grand scheme of things on how this is supposed to work. First, let's draw this picture. Okay. Here's a function that looks something like this. And we're going to have here and here. This is the x and this is the y. All right, this point right here is going to be x, and this is a function f, so this point over here is f of x. What we do next is we create a distance between this first point and some other point. We're going to call that distance h. If the distance between this point and this next point is h, what is the x-coordinate for this point? What is it? No. It's x plus h, right? Yeah, x plus h. Because you started at x and you went over h units. So starting at x, going over h, that is x plus h. What would be the y-coordinate up here?
F of x plus h.
Yeah, f of x plus h. Now, the key here is that the x plus h is all in the parentheses. You're taking the y value at the point x plus h. So it's all inside of that parentheses. All right, now, what we're going to do is we're going to find the tangent, the secant line, rather. That goes through there. So we want the slope of the secant line. And that would be the y-coordinate, which is this one, f of x plus h, minus the y-coordinate of the second point, f of x, divided by the first x-coordinate, so x plus h, minus the second x-coordinate, so x by itself. Now, So does everyone see that that's the slope of the secant line, using this is P and this is Q? Notice what simplifies. We have x plus h minus x in the denominator. So the x's cancel, and that leaves an h. Have you seen this before? Does this look familiar? What is this called? This is the difference quotient. That is the difference quotient. Yeah, the 8x's cancel here. So that is the difference quotient. The difference quotient is essentially the slope of the secant line. So we're going to need that. Now, what is our goal? Our goal is the tangent line. So in order to create the tangent line, you have to take this point Q and you have to bring it in, right? The tangent line only goes through point P. Tangent lines go through one point. Secant lines go through two. If I'm bringing this in, what's happening to my value of h? Getting smaller. How small do I need it to get? Well, no, h is a distance. Yeah, the h has to go to 0. All right. That's sort of a problem, isn't it? Because think about what happens here. If h is 0, right here, then this just becomes f of x. And then this is minus f of x, which is 0. But even worse, if h is 0, what's in the bottom? 0. Can we divide by 0? No. But the top would be 0 too, so that's okay. So what do we actually need to do? Take what? Take the limit. That's right. Since we want h to go to 0, and we can't really do it with the algebra, we substitute in the limit. And we want the limit is h goes to 0 of that thing. So, as h goes to 0, the slope of the secant line becomes the slope of the tangent line. And so the formula that we want here, sometimes called M-tan, is the limit as h goes to 0 of f of x plus h minus f of x over h. So that is the key. You start with secant lines, and then you take the limit to produce the slope of the tangent line. The slope of the tangent line is going to have a very high significance in this class. All right, so any questions on the theory behind all this? Recapping, you take Q that is a certain distance away on the x-axis, called h, and you squeeze Q down until it becomes P. When it becomes P, you can no longer use regular algebra because that's 0 over 0. So instead you use the limit. The limit will tell us what it would have been if the algebra actually worked. That's called the slope of the tangent line. Okay, let me show you an example. Find the slope of the tangent line of x squared at x equals 3 using the difference quotient. So, write out the formula for M-tan. That is the limit as h goes to 0 of f of x plus h minus f of x over h. The first thing we're going to substitute is the known value for x. The x is equal to 3 in this one. So where there is an x, I'm going to plug in 3. So this is 3 plus h minus f of 3 here over h. The function is x squared. So we will take everything that's in the parentheses here, right here, and we will plug that into the square function. So that's going to be 3 plus h squared minus, on the right side we have f of 3. So we take 3 and we square it. That is over h. Next, we need to multiply out 3 plus h. I believe I gave you a little shortcut trick, if you recall the other day. You square the 3, then you do 3 times h times 2, that's 6h, and then h squared, minus 9 over h. Alright. What cancels?
The 9s.
9s cancel. And that leaves me with the limit as h goes to 0 of 6h plus h squared over h. What factors? H. So this is 6 plus h times h divided by h. What cancels? H. So now the limit as h goes to 0 of 6 plus h. Now, at that point, and all through this, you're just doing a regular limit. At each point, you had h in the bottom. H was going to 0, so you could not plug it in. We just canceled the h's. So now, what do? Plug it in. So it's 6 plus 0, which is 6. So the slope of the tangent line would be 6.
When we write the answer down, do you want us to put like in hand or just or do
You can do it at the beginning, and that'll be fine. Let me show you what this looks like visually. Okay, I'm going to switch to the computer for a second. Let me get another one of these going here. So this was the parabola. All right. And then, let me just squeeze it over here like this. The slope of the tangent line was supposed to be 6. Okay. Then I'm going to use the transformation stuff that we know about here, which is that right there. Okay. Now, determine if that's the tangent line or not. Is it the tangent line? You bet. I mean, it looks like it overlaps a lot. That's just because the lines are really thick. But does everyone see how right here, this is the, what do we call this? Point of tangency. Okay? Remember that from the geometry? Just like that. You want me rescale this so it looks better? Let me do this here. Let's make this -1, 2, 5. And I'll make this a little bit steeper here. No. There. There. Does it look like a tangent line now? I bet it does. Yeah. Okay. That's what we're getting. Now, notice the importance here. Does everyone agree? Do you remember the algebra stuff about transformations and things? That if it's x minus a number, you're going to that point, then plus another number, that's the y part. This piece right here says go over to 3 and then up to 0.9. So, or up to the point where it's 9. So it's 3 and then 9. The part that we did the calculation on was the 6. That was our answer, right? Notice that if I change that 6, maybe to like an 8, that is not a tangent line. See how it doesn't, brace the function, right? It heads right on through the function. That is definitely not a tangent line. No, neither is -4. That's clearly not it, right? But 6 is the one that's it, right? When the function comes in, skirts off of it and everything else. All right. Questions? Now, what is this good for? Well, this thing is called the derivative. Let's give you the definition of derivative. The derivative of f of x is a function, number one, underline that, that's important. And the notation is this. The notation is f prime of x. So that little apostrophe, we read that as prime, f prime of x. That gives the slope of the tangent line to f at x. So the formula for derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. And then the last final note. The derivative exists if this limit exists. You can run into scenarios where the limit does not exist, and if the limit does not exist, then the derivative does not exist at that point. Okay. Now, the only difference between what we did in this last example and what we normally do is we went ahead and plugged in a value for x. We started off with x equals 3. And that's fine. That gives me the value at x equals 3, but that's all it gives me. What we're going to do in the future is we're going to create the entire function, so we will not replace the x in general. We'll leave it as x, and we'll come up with a formula, an expression, with x's in it. And then we take that formula, and then we plug in whatever x we want. We want 3, we want 4, whatever we want. Okay? Several of your homework examples will ask you to find the derivative, and then find f prime of 1, f prime of 2, f prime of 3. The process of doing the difference quotient and the limit is called the 4-step process. You can look that up in the book if you want, but that's what our textbook is calling it. When it says use the 4-step process, they want you to make this calculation. Simply put, the 4-step process that they talk about is compute this by itself, then take that answer and then compute all of this, that's step 2, then take that answer and divide by h, that's step 3, and then step 4, take the limit. If you need to break it down like that, you're welcome to do that. We normally don't do that. But that's what they talk about when they say the 4-step process. But just remember, if you had to do f prime of 1, f prime of 2, f prime of 3, you wouldn't want to repeat this long process 3 times. You would do it one time with x, and then just plug in the x values to get your values. Okay. All right, let's do this example. find f prime of x when f of x is equal to x cubed, and then use that to find the slope of the tangent line when x is equal to -1. All right. So to start this, let's write out what the derivative formula is. So the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h Now I'm going to plug in the function, but I'm not going to plug in a value for x. I'm going to leave that till the end. So we're going to plug in x plus h into the function. So I'm going to use brackets here for this first part so you can see where the individual parts come from. We're plugging in x plus h into the cube function. So this is x plus h cubed. That's the first part. Minus f of x. Well, f of x is just x cubed by itself. So that's all of the second part. Over h. All right, at this point, I think we're going to take a small break over here and work out what this is. So x plus h cubed, I need to figure out what that is, and then I'll just plug in the result right there. X plus h cubed is sort of a long process to figure out. So we need to, we'll just do that on the side. How would you figure out what x plus h cubed is? Suggestions?
Do x plus h times x plus h and then get that first and then times that. The whole times x plus h.
Okay, so you want to write out all three of them, and then you want to do these two first, and then take that result and then multiply it by the third one. That's correct. Bingo. All right, so we'll do two at a time, and then we'll come up with an answer. So what is x plus h times x plus h? That's x squared plus xh plus h times x is hx, and then h times h is h squared. Are xh and hx the same? Yes. Yes, you can multiply in any order. So those are the same. So this is actually x squared plus 2hx plus h squared times x plus h. All right. Now to multiply this out, the way to multiply three terms, a trinomial by a binomial, is you just take every term in the first one and you multiply it by each of the terms in the second one. Okay? So we're going to do x squared times x, that's x cubed. Then we're going to do x squared times h, so that's x squared h. Now I move over to the 2hx, and multiply that by x. So that's 2hx squared. Then 2hx times h, that's 2h squared x. Lastly, h squared times x is h squared x. And then h squared times h is h cubed. I ran out of room. And then one more step. Which of these are the same and can be added together? Well, there's only one x cubed. What about h squared, x squared h? There's 1 here, and there are 2 right here. Right? So these are the same. And so how many total is that? That is 3 x squared h. I'll put the h on the back side here. Same thing here. These are the same, so that's 3 of those. And then we have h cubed, like so. And so that's how you multiply out x plus h cubed. So we'll substitute that into our limit. And so we get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed from the backside there over h. All right, what cancels? X cubes cancel. And that leaves me with the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed over h. What can you factor from the numerator? Yeah. So h comes out. That leaves from the first term 3x squared. From the second term, I'm going to have 3x, and I'm still going to have 1h left over here, so it's 3xh. And factoring from the last term here, that's going to give me h squared over h. What cancels? H's cancel. That is the key. You have to get the h's to cancel somehow. If they can't cancel, you're not going to be able to take the limit. 3x squared plus 3xh plus h squared. We have gotten rid of the h in the bottom, so we can now evaluate the limit by plugging in h goes to 0. So this is 3x squared plus 3x times 0 plus 0 squared. Remember, this is a limit with h as the variable, so it's only the h's that go to 0, not the x's. And then that's 0 and that's 0, so the result is 3x squared. So that is the derivative. So f prime of x is equal to 3x squared. Again, the derivative is a function, right? Now, you may do some of these and get numbers, but that just means it's the function that is always that number. It's the constant function. But in general, you should get a function with x's for the answer. Now, the second part of this question was to find the slope of the tangent line when x is equal to -1. So this is f prime of -1. You have to be very careful when you write these. This is not f of -1. It's f prime of -1. So it's going to be 3 times -1 squared. -1 squared is 1, so f prime of -1 is 3. So the slope of the tangent line to y equals x cubed at x equals -1 is 3. Okay, you have some extra paper? Let's do another one. That's not in the notes. And a reminder, one of the first steps is to plug in x plus h. There are two places to plug in x plus h. Those are two x's. All right, work that with the partner real quick. X is equal to the limit as h goes to 0. And I'm going to show you this formulation as well. If it's a g function, then it's not f of x plus h. No, it's g of x plus h minus g of x. Again, the f and the g, they're just function names. So here for this one, the relative function name is a g. No big deal. So here we're going to apply g of x plus h. In the function g of x, the x is entirely in the square root. That means when we plug in x plus h, we're going to put x plus h entirely in the square root, as opposed to it being the square root of x and ending the square root and then putting the plus h on the outside. No, the whole quantity x plus h goes on the inside. G of x is the square root of x, and then we have an h. Now this problem differs a little bit from the ones that we've done in the past, because the goal has always been to do some algebra manipulation, like multiplying things out and then canceling some stuff and then factoring. Here we can't factor out an h. We can't split up the square root, right? You can't split up square roots over addition. That's not possible. Okay? So we have to employ another little algebra trick. And this little trick is called the conjugate. Okay? The conjugate is when you take something that is, let's say, a minus b, and you turn that into a plus b. In other words, you change the sign of the in the middle, right? But you only change one sign. Here I have something that is sort of a plus b or a minus b. And so what we're going to do is we're going to multiply this by the conjugate of this numerator. So it's going to be x, the square root of x plus h plus the square root of x. Now, as I mentioned previously, you can't just go willy-nilly multiplying by stuff. What's the only number you can multiply stuff by that doesn't change the expression? 1. So how do we get a 1 here? We multiply on both the top and the bottom. All right. So here we go. And we're going to multiply the first one and the first one here. So the square root of x plus h times the square root of x plus h is x plus h. Because the square root of a number times the square root of the same number is just that number, right? Next, we'll do the square root of x plus h times square root of x. That is the square root of x times x plus h. So numbers that are on the inside of a square root, you can multiply those together. Next, I'm going to do this one and then that last one. So minus the square root of x times the square root of x plus h. So that's minus the square root of x times x plus h. And then lastly, negative square root of x times square root of x. That is minus x. All that is over h times the square root of x plus h plus the square root of x. And again, we're going to save the bottom. We're not going to multiply that out yet. We'll see what we can get to happen with that. All right, take a look at the numerator. And tell me what cancels. Yeah, everything but the h, right? The square roots cancel because they're opposites and the same square root. And then on the left we have x, and way over here we have minus x. Now it's in parentheses, but it's not being multiplied by anything else, so that's okay. We're going to cancel that one, and we're going to cancel the one on the end. And what do we have? This is the limit as h goes to 0 of h over h times the square root of x plus h plus the square root of x. What cancels? The h is canceled, like so. And so this is equal to the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now we still have an h in the denominator, but it is being added to the x. So as h goes to 0, we do not get a 0 factor. So we can go ahead and run the limit through here. And this is the square root of x plus 0 plus the square root of x. X plus 0 is x, so this is the square root of x plus the square root of x, and the square root of x plus the square root of x is plus, not multiply. Yeah, it's two of them, 2 square roots of x, yeah. And so that's the derivative there. And then the second part of this problem was to evaluate and find the slope of the tangent line when x is equal to 9. So that would be g prime of 9, which is 1 over 2 square roots of 9. The square root of 9 is 3. 3 times 2 is 6, so that's 1 over 6. Sort of ran out of space here to do that one. That's 1 over 6. So here are some examples of where you cannot find the derivative. On this first graph, the derivative at x equals c does not exist. Okay? And it does not exist because the graph is not continuous. So not continuous implies not differentiable. In other words, if you tried to find f prime of this graph, which you could do at the other points, but then if you tried to find f prime of c, you don't get an answer. It's undefined or it does not exist. Remember where all this stuff comes from. It comes from the limit. Okay. The second graph, this one is not differentiable at this point c because of the sharp corner. Remember that you're taking the slopes on one side and the slopes on the other side. The slopes on the left have to sort of morph into the slopes on the right. At this graph here, at x equals c, they abruptly change, which you can't have. Okay? So this one is not differentiable because of sharp corner. Okay. The third one is not differentiable because you have a vertical tangent line at x equals c here. So, and the connection here to make is that the derivative evaluated at a point refers to the slope of the tangent line. If you have a vertical line, a slope of a vertical line is undefined, Since the derivative is the slope of the tangent line, then the slope is undefined, so the derivative is undefined. And lastly, you cannot have a cusp. This little shape here is called a cusp. A cusp also leads to a vertical tangent line. All right, so how do you actually know when you don't have a function that is differentiable at a point? Here's a good example. F of x is equal to the absolute value of x. We want to show that f prime of 0 does not exist. And we're going to do it with the difference quotient, and then we'll do it by doing the sketch. So if you want to do the difference quotient on this one, we have already chosen the value for x. So instead of doing this in general, we're going to do this at x equals 0. So it's f of 0 plus h minus f of 0. We did an example like this when we first started doing difference quotients with derivatives. We plugged in the x value of the one that we wanted. In general, this is a bad idea, but we need it to show that it doesn't exist because the derivative only doesn't exist at one point. This is the limit as h goes to 0. 0 plus h is h, and the function is the absolute value function. So this is the absolute value of h minus the absolute value of 0 over h. This is the limit as h goes to 0. The absolute value of 0 is 0, so that part goes away. And this leaves me with the absolute value of h divided by h. Well, that's our old friend from the test and from the notes and everything else. And we know from prior experience that this limit does not exist. Since the limit does not exist, that then implies that f prime of 0 does not exist. Okay. So that's how you would show that a limit, that a function is not differentiable at a certain point by trying to find that limit, and then it doesn't work. The last part of the directions here were to draw the sketch and monitor the slopes. So we know that the absolute value of x looks like this, right? Straight lines on both sides. If you look at the slope of the tangent line on this side, they're all positive ones. Even as you get closer and closer to 0, they're all positive ones. On the left side, what are all the slopes? They're all negative ones, right? And there is no place where it just suddenly starts to morphize into from -1 to 1. They're all -1, and they're all 1. And so at 0, on the left side it should be -1, on the right side it should be +1. So that means the limits don't exist because the two one-sided limits are not the same.